Hi, I'm Christi Chavez, and today I'll be covering Golden Gate Assembly for my Fall 2023 Advanced Microbiological Research Methods First Local Expert Project. We've gone over some methods of DNA assembly in class already. We've touched on Gibson assembly and CRISPR, but today I'm going to attempt to share with you what I've learned about Golden Gate assembly. Let's look at how Golden Gate assembly compares with other DNA assembly methods. With Gibson and CRISPR, there's recombination of homologous sequences at the ends of the DNA fragments in order for assembly to occur. This infographic was from a lecture, and I just thought it was very, very well done in showing your linear vector with your inserts, the homology that they have to each other, and the homology that they have to the vector, and then your transformed vector. And I just found this infographic really helpful, and I wanted to include it. Shows how homology and the homologous arms are very important to Gibson assembly. And then in this example, it shows the CRISPR-Cas9 system employing homology-directed repair. Some limitations of the CRISPR and Gibson assembly systems compared to Golden Gate assembly are that you do need at least 15 nucleotides to be homologous with the ends of the DNA fragments. Sometimes the homology needs to be 50 base pairs or longer, so you must carefully design your primers. Whereas with Golden Gate assembly, you only need homology of the ends of the DNA fragments. You just need 4 of the same nucleotides flanked by type 2S restriction enzyme sites. So in figure 1A, we are looking at the digest of 2 DNA fragments that have the same 4 nucleotide sequence. F stands for fusion site. And these 4 nucleotide sequences are flanked by BPI restriction sites in this example. The digestion leads to the generation of complementary overhangs. The ligation of these fragments leads to it lacking the original type 2S restriction site in the new construct. In part B, it's very similar but it shows the restriction sites changing upon ligation. You can see it's using BPII, BSAI, back to BPII. Here, P stands for promoter, CDS is the coding sequence, and T is the terminator. And then this is showing you the new construct that would then use a new restriction site and a new restriction enzyme to ligate. Oh, let me go back here. These type 2 restriction enzymes can cleave outside their recognition sites, creating 4 base flanking overhangs. Any 4 nucleotides can be the site of cleavage as long as they have the same sequence and are flanked by type 2S restriction sites. The fragments of DNA with compatible restriction sites can be digested and ligated with no scars because each cloning step results in a construct that lacks the restriction sites for that type 2's enzyme. This means that subsequent assemblies with that construct will need to use a different type 2S enzyme. Figure 2 is showing almost the same thing, but in this starting sequence, there are 2 type 2S restriction sites, BPII and SAI, and those sites are then mutated with two nucleotide substitutions. F2 and F3 are shown in gray, and they are fusion sites. F1 and F4 are shown in black, and they are standard fusion sites of standard sequence, and those need to be compatible with the ends of the vector. And here you can see everything coming together into the destination vector and the final construct. Figure 3 is showing those sites that are mutated with the two single nucleotide substitutions, and they simplified this figure. It's only showing the single BPII site. The mutation and the fusion site do not overlap here, but that is fine. That is all the time I have for today. Thank you, and I hope this was informational.